Okay, last video over chapter 2, uniform acceleration. So this is the simplest form of acceleration and just kind of is occurring because there's like a constant force that's acting on the object. You know, your car is moving because you're pushing the gas, which is causing force in the tires to hit the pavement, and it's just constant force that's causing your vehicle to move. And you could come up with a lot of other examples. They're saying a falling rock or a falling object or a car accelerating at a constant rate. So, for example, a car moving along a straight road and speeding up at a constant rate would have a constant acceleration. So this means that it's just constantly speeding up when it has this constant line right here. Notice this isn't a V versus T or a D versus T, it's an A versus T. So a constant acceleration. Now, for this example, it's showing the car starts out with 0 initial velocity. So now we have a V versus T. So then the velocity increases at a steady rate. So in order to find the acceleration here, we would do, or we could do anyway, we could take the slope by doing the change of velocity over time. Well, remember the change of velocity is final minus initial over time. So we could find any 2 points on here. This would be my final, this would be my initial, and then whatever amount of time this is from this point to this point is how I would find that acceleration. Another way of writing this same equation is solving for that. So if I was to solve for that using algebra, so let me rewrite this really quick. How could I solve for that using algebra? Well, I got to get rid of this denominator here. So how do you get rid of a denominator? Well, you multiply by the denominator. So now it looks like this. T times A is equal to VF minus V initial. Now how do I get this initial velocity over to the other side? Well, I add it. So it's like T times A is equal to final, or didn't add my initial, did I? So after it's all said and done, you typically will put what you're solving for on the left side of the equation. So you have V is equal to VO, which is initial, plus AT. So this is one of our equations, okay? This equation right here is the exact same as that equation, all right? So this is what's known as a kinematics equation in physics, and they write it out where there's no fractions involved, which is kind of nice. Okay, I must have an example since I have a blank slide here. Let me see. Yeah. Okay. Oh, I don't know that we're quite to this yet, though. Yeah, maybe. Maybe not part B. So this is page 31, and it's example 2.4. So this says that a car travels due east with an initial velocity of 10 meters per second, and it accelerates for 6 seconds at a constant rate of 4 meters per second squared. So remember, whenever it has meters per second squared, that's a unit for acceleration. So it's wanting us to find the velocity at the end of this time. So it wants us to find final velocity. Well, this is the kinematics equation that we just had, right? So what is our initial velocity? It was 10 meters per second, plus our acceleration, which was 4 meters per second squared, times 6 seconds. So get your calculator if you need to. 4 times 6, 24, plus 10, 34. So it's 34 meters per second is your final velocity at that point. I think we need to go to the next slide because it's going to give us another equation that we need for part B on that last example. So this is a distance versus time graph again for uniform acceleration, so meaning that it's constantly increasing, okay? And as it gets farther along the distance, it looks like it's increasing more. How do you know that? Because you could just make a little, you could do your slope here at every point, and you can just see that, I didn't draw this one very good, this second segment, but you can see that it just constantly gets steeper the farther along it goes, okay? So whenever you have something like that, and you want to figure out what the distance, the total distance is, you can use this other kinematics equation, which is distance is equal to 1/2 AT squared. So this is distance, and that of course is acceleration, and then you have time squared, okay? And they kind of show you another bit of it as well. So here, basically what they're doing is they're taking the area under again to find the distance. So you've got your initial velocity times time. So length times width, essentially. VO times time. But then it has this sort of triangle situation. So that's where it has this 1/2 base times time squared that's happening. So for this, it wants you to know that it's possible that you could have to know the initial velocity plus the time, or times the time, plus 1/2 AT squared. So this is also what's called a kinematics equation. Now in physics, we get into a little bit more of how we get these equations, and they're just basically figured from equations that we already know, like velocity is distance divided by time, and we have our velocity equation, but that's just a lot of information. So you will get this equation given to you. You just need to know when to use it. So we're gonna go back to that example that we had a couple slides ago and see what part B says now. So part B says, how far does it travel during this time? So anytime it asks us to figure out how far, it's wanting us to find distance. Okay, well, we just had two equations for that. Oops, that was 1/2. My bad. And we had this one. Okay, well, if you ever have an example that the initial velocity was just 0, it was at rest, then you would use this first one. But was our initial velocity 0 in this particular example? No, we started at 10 meters per second. So we have to use the second one. So we have 10 meters per second times that 6 seconds plus 1/2, and the acceleration was 4 meters per second times 6 seconds squared. So once you get all of that put in, you're going to want to make sure that you know how to do all of this, you know, as far as plug it into your calculator correctly. If it were me, I would say to do the 6 squared first on your calculator and kind of work backwards. So do 6 squared times 4 times 1/2, which is 72. And then maybe write that down. And then you've got 10 times 6, which is of course 60. So then you can add those up. 60 plus 72, 132. we're finding distance, what do you think the unit's going to be for this? You measure distance in meters in science or the metric system. So our distance is going to be meters, 132 meters. Okay. Hopefully that's making some sense. Let's see if we can answer some of these questions really quick. Okay, so we've got this. The velocity of a car increases with time as shown. What is the average acceleration between 0 seconds and 4 seconds? Okay, so how could I find that? Well, acceleration is final velocity minus initial velocity over time. Well, what was our final velocity from this point to this point? Well, velocity is over here on the y-axis, right? So it's 4. So we had 4 meters per second. What was our initial velocity? 0 over 4 seconds minus 0 seconds. So you have 4 meters per second over 4 seconds, which is 1 meter per second squared. See, you had 4 meters per second over 4 seconds, which is 1 meter per second squared. So E would be your correct answer on that one. All right, this says, what is the average acceleration between 4 and 5 seconds? So I would encourage you at this point to maybe pause, try to work it out on your own, and then play and see if you get it correctly again. So if you're just going along with me, you've got 12 meters per second minus 4 meters per second. Oops. This pen is so weird sometimes. Okay, over 5 seconds minus 4 seconds. So you should end up with 8 meters per second squared, which is C. Okay? Easy enough on that? All right. This one says, what is the average acceleration between 0 seconds and 5 seconds? So, how would you go about doing that one? Well, it's the same. Your final velocity was 12. Your initial velocity was 0. 5 seconds minus 0 seconds. So 12 divided by 5 is 2.4 meters per second squared. So that was like doing this between 0 and 5 seconds. Okay? Now, this one says that the velocity of a car increases with time as shown. Why is the average of the average acceleration from 0 to 4 and 4 to 5 different from the average of 0 to 5? Well, obviously, whenever we do, it's kind of like the same thing that we did on the one video with the total average speed or velocity. This is just showing us the average acceleration. So if you do between two different points within the graph, it could be different. But overall, it should be around, 2.4 between the 2 points that you found. Okay. Oh, it starts all over again for some reason. Weird. Instead of just ending. So that is the end of chapter 2. If you guys have any questions at all about these things, if you're not understanding something, please don't hesitate to email or to get a hold of me on Remind so that we can kind of go through some of it together.